All right, let's go. Number 10, ram pressure stripping, the invisible force that rips galaxies apart as they fall through clusters. When we think about what can destroy a galaxy, our minds naturally jump to spectacular, violent events, collisions, explosions, the gravitational fury of supermassive black holes. But one of the most efficient and most merciless galaxy killing mechanisms in the universe operates through a process so quiet, so gradual, and so invisible that it went unrecognized for decades. It is called ram pressure stripping, and it does not smash galaxies, it bleeds them dry. When a galaxy falls into a galaxy cluster, pulled inward by the immense gravitational well of hundreds of other galaxies and their surrounding dark matter halos, it does not fall through empty space. The space between galaxies inside a galaxy cluster is filled with a diffuse, superheated plasma called the intercluster medium, reaching temperatures of tens of millions of degrees and permeating the entire cluster volume at densities far above the intergalactic average. As the infalling galaxy plunges through this hot plasma at speeds of hundreds to thousands of kilometers per second, it experiences a hydrodynamic ram pressure, the same physical principle that strips a flag from a flagpole in a hurricane, but operating on a galactic scale and with unimaginable force. The ramp pressure acts on the cold gas inside the infalling galaxy, the interstellar medium of gas and dust from which new stars form, but not on the stars themselves, which are gravitationally bound to the galaxy's dark matter halo. The result is a systematic directional stripping of the galaxy's raw star-forming material, pulling it out of the galaxy like a comet's tail and depositing it in a long, trailing stream behind the galaxy as it moves through the cluster. Galaxies caught in this process, called jellyfish galaxies because of the trailing tendrils of stripped gas visible in deep imaging, are being robbed of their future. Without cold gas, no new stars can form. The galaxy's stellar population ages, reddens, and fades over billions of years without replacement. Ramp pressure stripping does not explode a galaxy. It quietly removes its ability to sustain itself, leaving behind a red, dead elliptical, a galaxy-sized graveyard of aging stars with no fuel to produce a next generation. Clusters of galaxies are, in this sense, graveyards that actively accelerate their own filling. Number 9. Active galactic nucleus feedback at maximum power, when a galaxy's own black hole declares war on its host. A supermassive black hole at the center of a galaxy, when actively feeding, is capable of releasing energy at a rate that exceeds the gravitational binding energy of the entire galaxy on timescales of tens to hundreds of millions of years. This is not a theoretical limit. It is something astronomers observe directly in multiple systems at multiple cosmic epochs, in a process called AGN feedback that represents one of the most dramatic and consequential galaxy-scale phenomena in the observable universe. The mechanism operates through two distinct channels. In the first, called quasar mode feedback, the accretion disk surrounding a rapidly feeding supermassive black hole radiates so intensely that radiation pressure drives a galaxy-wide wind of gas outward at thousands of kilometers per second, sweeping the interstellar medium out of the galaxy entirely and terminating star formation across the entire galactic disk simultaneously. This is a process operating in SDSS 1106 plus 1939, covered in a previous video, which is expelling gas at 2 trillion times the sun's luminosity and kinetic power. In the second channel, called radio or jet mode feedback, a spinning black hole launches relativistic jets that couple their energy to the surrounding hot gas halo, heating it and preventing it from cooling and falling back into the galaxy to form new stars. What makes AGN feedback at maximum power a true galaxy destroyer is its irreversibility. Once the cold gas reservoir of a massive galaxy has been ejected by a quasar wind, the gas disperses into the intergalactic medium at velocities too high for the galaxy's gravity to recapture it. The galaxy is permanently and completely quenched, its star formation terminated, not gradually, but abruptly, on timescales of tens of millions of years, by the energy released by the very black hole that grew inside it. The most massive galaxies in the universe, the giant ellipticals that anchor the centers of galaxy clusters, owe their red, dead, starless nature almost entirely to this process. They were not always dead. They were killed by their own central engines, which grew large enough and fed rapidly enough to turn on their hosts with enough energy to end star formation across structures containing hundreds of billions of stars, permanently and completely, in a cosmological instant. Number 8. Gravitational tidal stripping and dense environments. How galaxy clusters dismantle galaxies piece by piece over billions of years. Ram pressure strips gas, but galaxy clusters possess a second, slower, and in some ways more thorough mechanism for dismantling their member galaxies. Gravitational tidal stripping, the process by which the combined gravitational field of the cluster, dominated by its dark matter halo containing masses of hundreds of trillions of solar masses, progressively pulls stars, star clusters, and dark matter itself away from individual galaxies orbiting within it over billions of years of repeated passages through the cluster's dense central regions. Unlike ram pressure stripping, which acts only on gas, gravitational tidal stripping acts on every component of a galaxy. Stars, dark matter, globular clusters, satellite dwarf galaxies, without discrimination. As a galaxy passes close to the cluster center on a highly eccentric orbit, the difference in gravitational force between the near side and far side of the galaxy, the tidal force, exceeds the self-gravity holding the galaxy's outer regions together. Stars and dark matter in the galaxy's outskirts are pulled free and deposited into a diffuse stellar halo surrounding the entire cluster, contributing to a population of intra-cluster stars that belong to no individual galaxy but drift freely through the cluster's potential. Over multiple orbital passages spanning billions of years, a galaxy can be reduced to a fraction of its original size and mass through this process. The most extreme product of prolonged tidal stripping is an ultra-compact dwarf galaxy, an object the size of a large globular cluster but with the mass of a small galaxy, representing the surviving dense core of a formerly normal galaxy that has had its outer regions completely stripped away by repeated tidal interactions over the period of billions of years. Galaxy clusters are not merely passive containers of galaxies. They are active processing environments that reshape, reduce, and ultimately destroy the galaxies unfortunate enough to fall into them. Number 7. Lyman break galaxy superwinds, the most powerful galactic outflows in the history of the universe, operating at cosmic dawn. In the early universe, between approximately 1 and 3 billion years after the Big Bang, a period astronomers call cosmic noon because it represents the peak of both star formation and black hole accretion across the observable cosmos, a population of galaxies that existed that were doing something that no galaxy in the modern universe approaches in terms of raw, sustained destructive power. These were the Lyman break galaxies and their cousins, the sub-millimeter galaxies, compact, intensely star-forming systems converting gas into stars at rates of hundreds to thousands of solar masses per year, powered by star formation rates hundreds of times higher than anything seen in the Milky Way today. At these extreme star formation rates, the death rate of massive stars, exploding as supernovae after just a few million years of life, was correspondingly extreme. Thousands of supernovae detonating per year in a compact galactic volume inject energy into the surrounding interstellar medium at a rate that overwhelms the galaxy's ability to radiate it away or absorb it gravitationally. The result is a galactic superwind, a collective galaxy-scale outflow driven by the combined mechanical energy of thousands of simultaneous supernova explosions, launching the interstellar medium outward at velocities of hundreds to over 1,000 kilometers per second. Spectroscopic observations of Lyman break galaxies at redshifts between 2 and 4, when the universe was between 2 and 3 billion years old,
routinely detect absorption features blue shifted by hundreds of kilometers relative to the galaxy's systemic velocity, the unambiguous spectroscopic signature of fast-moving outflowing gas intercepting the background light of the galaxy itself. The mass outflow rates in the most powerful systems approach or exceed the star formation rates, meaning these galaxies are ejecting gas into the intergalactic medium as fast as or faster than they are converting it into stars. They are self-terminating, consuming and expelling their own fuel supply simultaneously, building toward an inevitable quenching when the last cold gas reservoir is either converted to stars or blown into the intergalactic medium beyond recovery. The early universe was full of galaxies destroying themselves through the sheer violence of their own productivity.
Number 6. Intergalactic magnetic fields and their role in permanently suppressing galaxy formation, the invisible architecture that decided which parts of the universe would ever contain galaxies and which would remain permanently empty. The large-scale structure of the universe, the cosmic web of filaments, sheets, and voids that organizes the distribution of matter across hundreds of millions of light years, is primarily shaped by gravity and dark matter, but threaded through this gravitational architecture and increasingly recognized as playing a significant role in determining which regions of the universe ever form galaxies and which remains permanently empty, is a component that is extraordinarily difficult to observe, and whose origin remains one of the outstanding mysteries in cosmology: the intergalactic magnetic field. Observations using Faraday rotation measurements of background radio sources, a technique that measures how polarized radio waves are rotated as they pass through magnetized plasma, have established that the filaments of the cosmic web are permeated by magnetic fields with strengths of the order of nanogauss to microgauss, coherent over scales of millions of light years. The voids between filaments appear to contain even weaker fields, potentially at the femtogauss level, whose origin is genuinely unclear. They may represent a primordial magnetic field generated in the very early universe before any stars or galaxies existed to produce magnetic fields through conventional astrophysical processes. The relevance of these intergalactic magnetic fields to galaxy formation and destruction is direct and significant. Magnetic pressure resists the compression of gas, supplementing thermal pressure in opposing gravitational collapse. In regions where the intergalactic magnetic field is strong enough, gas that would otherwise cool, collapse, and form a galaxy is held up by magnetic pressure and prevented from doing so. Magno-hydrodynamic simulations of cosmic structure formation that include realistic intergalactic magnetic fields produce a suppression of low-mass galaxy formation, particularly in filaments and at the outskirts of clusters, that better matches observations than purely gravitational and thermal models. The magnetic architecture of the cosmic web is not merely a passive bystander to galaxy formation. It is an active participant that has been quietly deciding since the earliest epochs of cosmic history which clouds of gas would ever be permitted to collapse into galaxies and which would be held in permanent suspension by an invisible magnetic barrier spanning millions of light years. Number 5. Galaxy harassment. The death by 1,000 high-speed encounters that transform spiral galaxies into dwarf spheroidals. In the dense environments of galaxy clusters, individual galaxies do not simply orbit peacefully around the cluster potential and occasionally undergo one dramatic collision. They experience a continuous, relentless series of high-speed gravitational encounters with other cluster members. Brief, impulsive interactions that individually produce only minor perturbations, but that accumulate over billions of years of cluster membership into a transformative process that fundamentally and permanently alters the structure, stellar populations, and morphological type of the affected galaxy. This process was identified and named galaxy harassment by astronomers Ben Moore, Lake, and Katz in 1996, following high-resolution N-body simulations of galaxy orbits within clusters. The key distinction between harassment and a simple merger is velocity. In the field, outside of clusters, galaxy encounters occur at velocities comparable to the internal rotation velocities of the individual galaxies, allowing the two systems to gravitationally capture each other and merge over extended timescales.
Inside clusters, the velocity dispersion of member galaxies is hundreds of times higher than the internal velocities of individual galaxies, meaning encounters are too fast and too brief for gravitational capture. Instead, each high-speed flyby delivers an impulsive gravitational kick to the target galaxy, injecting kinetic energy into its stellar orbits and heating the stellar system dynamically. Over hundreds of such encounters across billions of years of cluster membership, a late-type spiral galaxy, a rotating disk of stars and gas like the Milky Way, is progressively heated, thickened, and stripped until it bears no resemblance to its original form. The disk structure is destroyed as stars are kicked on random non-circular orbits. The gas is stripped by ram pressure simultaneously. The resulting object is a pressure-supported, gas-free, featureless spheroidal system, a dwarf spheroidal galaxy, the most common galaxy type in the observable universe by number, bearing no trace of the organized, star-forming spiral galaxy that entered the cluster billions of years ago.
Number 4. Cooling flow instabilities in galaxy cluster cores, when the hot gas holding a galaxy together begins to catastrophically collapse. At the centers of the most massive galaxy clusters in the universe, the intracluster medium, the hot X-ray emitting plasma filling the space between galaxies, reaches its highest densities. At these densities, the cooling time of the plasma through X-ray emission becomes shorter than the age of the cluster, creating what was once called a cooling flow, a predicted inward flow of cooling gas toward the cluster center. As the plasma loses energy, cools below X-ray emitting temperatures, and presumably condenses into cold molecular gas, and eventually forms new stars. The problem that dominated cluster astrophysics for 2 decades starting in the 1990s was that cooling flows do not produce the predicted quantities of cold gas and star formation. Deep X-ray observations of cluster cores showed gas cooling from tens of millions of degrees down to a few million degrees, but then apparently stopping, failing to cool below a threshold of approximately 10 million Kelvin, and failing to produce the hundreds of solar masses per year of new stars that simple cooling flow models predicted. Something was reheating the gas and preventing the catastrophic cooling collapse that the simple thermodynamics demanded. The answer, confirmed through X-ray and radio observations across dozens of clusters, is AGN feedback from the central dominant galaxy's supermassive black hole, the same mechanism described earlier but operating in a specific feedback-regulated mode in which the black hole's jets inflate enormous bubbles of relativistic plasma in the intracluster medium, heating the cooling gas through a combination of shock heating, sound wave dissipation, and turbulent mixing. This feedback loop, gas cools, falls toward the black hole, feeds it, energizes jets, jets heat the gas stops cooling, operates in a precise self-regulating balance in most clusters. But the balance is not guaranteed. In certain systems, the cooling rate temporarily overwhelms the AGN heating, or the AGN enters a low activity phase, allowing a runaway cooling instability to develop. When this occurs, thousands of solar masses per year of cold molecular gas rain down onto the cluster core, triggering explosive star formation episodes and dramatically disrupting the thermal structure of the surrounding intracluster medium across scales of hundreds of thousands of light years. Number 3. The Phoenix Cluster, the single most violently star-forming system in the observable universe, and what it reveals about galaxy destruction. At a distance of approximately 5.7 billion light-years in the constellation Phoenix sits a galaxy cluster so extreme in its properties that it has forced a fundamental revision of theoretical models of how clusters evolve and how the most massive galaxies in the universe regulate their own growth. It is simply called the Phoenix Cluster, and it contains the brightest X-ray emitting intracluster medium ever detected, the most powerful cooling flow ever confirmed, and at its center, a galaxy producing new stars at a rate of approximately 800 solar masses per year, roughly 800 times the star formation rate of the Milky Way, sustained continuously for hundreds of millions of years. The Phoenix cluster represents a case where the AGN feedback mechanism that normally regulates cooling in cluster cores has temporarily failed or been overwhelmed. The central galaxy's supermassive black hole,
itself one of the most massive known, with a mass estimated at tens of billions of solar masses, is simultaneously among the most powerful AGN ever observed in terms of jet power, and among the most actively star-forming central cluster galaxies ever identified. The cooling flow is depositing cold molecular gas onto the central galaxy faster than the AGN can heat and expel it, producing a runaway episode of star formation whose duration and eventual termination are currently being actively debated. What the Phoenix cluster demonstrates at galaxy-destroying scales is the consequence of a failure in the self-regulating feedback loop that normally keeps cluster cores stable. The enormous quantities of cold gas raining down onto the central galaxy are simultaneously feeding the supermassive black hole to unprecedented levels of activity, and triggering star formation at a rate that will, over hundreds of millions of years, convert the equivalent of hundreds of billions of solar masses of gas into stars. This single galaxy cluster core is processing more gas into stars per year than entire galaxy groups, and the eventual exhaustion of that cold gas reservoir, combined with the energy injection from the by then enormously fed central black hole, will terminate the episode and leave behind a central galaxy transformed in mass, structure, and stellar population by an episode of cosmic excess that has no parallel in the modern universe.
Number 2. Dark matter halo evaporation. The process by which galaxies are stripped of the invisible scaffolding that holds them together. Every galaxy in the universe is embedded in a halo of dark matter, an invisible, non-interacting mass distribution extending far beyond the visible stellar body of the galaxy, containing several to dozens of times more mass than the galaxy's stars and gas combined. This dark matter halo is not merely a passive gravitational backdrop, it is the structural foundation upon which the galaxy is built. It is the gravitational well into which gas cooled and condensed to form stars in the first place. It is the scaffolding that maintains the coherence of the galaxy's stellar orbits against the tidal forces of the external environment. Without its dark matter halo, a galaxy is not merely diminished, it is structurally compromised at the most fundamental level. In the dense gravitational environments of galaxy clusters, dark matter halos are not safe. The combined tidal field of the cluster, the same field that strips stars from individual galaxies through gravitational tidal stripping, also strips dark matter from the outskirts of individual galaxy halos, transferring it to the diffuse dark matter halo of the cluster as a whole. This process, confirmed through gravitational lensing analyses of galaxy members and through N-body simulations of cluster evolution, progressively reduces the dark matter halos of cluster galaxies over billions of years of cluster membership, stripping them from the outside inward and removing the gravitational scaffolding that maintains the galaxy's structural integrity. The most dramatic consequence of dark matter halo stripping is observed in the ultra-diffuse galaxies, extremely low surface brightness objects with the physical size of normal galaxies, but stellar masses 100 to 1,000 times lower, spread across enormous volumes with such low densities that they are nearly transparent. Dozens of ultra-diffuse galaxies have been identified in nearby clusters, most famously the Coma cluster, and their properties are consistent with galaxies that have been almost completely stripped of their dark matter halos, leaving behind only the loosely bound stellar populations that have survived the loss of most of their gravitational foundation. They are galaxies in the process of dissolving, their dark matter stolen, their stars slowly dispersing, their identity as coherent gravitational structures fading over billions of years into the featureless stellar background of the cluster. Number 1. Supermassive black hole recoils when gravitational wave emission launches a black hole through its own galaxy at thousands of kilometers per second. When two supermassive black holes merge, the final stage of a galaxy merger, after billions of years of orbital decay and gravitational wave emission have brought the two black holes to within a few parsecs of each other, the merger event itself releases the most energetic burst of gravitational radiation in the observable universe. But the gravitational wave emission is not isotropic. It is not the same in every direction. Depending on the mass ratio and spin orientations of the two merging black holes, the gravitational waves emitted preferentially in one direction carry more momentum than those emitted in the opposite direction. By Newton's third law, the merged remnant black hole recoils in the direction opposite the strongest gravitational wave emission, kicked away from the merger site by a rocket-like reaction to its own gravitational wave output. For mergers of equal mass, aligned spin black holes, this gravitational recoil velocity is modest, a few hundred kilometers per second, insufficient to escape the gravitational potential of a massive host galaxy. But for mergers involving unequal mass and misaligned spins, configurations that are physically plausible and perhaps common in the real universe, numerical relativity simulations predict recoil velocities of thousands of kilometers per second. The maximum predicted recoil for the most favorable spin configurations approaches 5,000 kilometers per second, more than sufficient to launch the merged supermassive black hole completely out of its host galaxy and into intergalactic space. A supermassive black hole ejected from its host galaxy at thousands of kilometers per second carries with it several consequences that operate at galaxy-destroying scales. First, the ejection removes the supermassive black hole that was regulating the galaxy's star formation through AGN feedback. Without its central black hole, the galaxy loses its self-regulating heating mechanism that prevented runaway cooling flows and may subsequently experience an uncontrolled burst of star formation, followed by complete gas exhaustion. Second, the ejected black hole, traveling through the galaxy at thousands of kilometers per second, gravitationally perturbs stellar orbits across the entire galactic nucleus as it exits, scattering stars and disrupting the nuclear star cluster in a process that permanently alters the central structure of the galaxy. Third, and most devastatingly, the recoiling black hole carries with it an accretion disk of gas that continues feeding it for millions of years after ejection. A hypervelocity quasar moving through the galaxy, injecting AGN energy into the interstellar medium from a rapidly moving, uncentered source that cannot be counteracted by the galaxy's remaining gravitational structure. The galaxy's own merger, the event that was supposed to build a larger, more massive system from the two progenitors, instead ejects the combined engine of both into the void, leaving behind the galaxy decapitated at its core, structurally disrupted across its nucleus, and stripped of the regulatory mechanism that determined whether it would live or slowly die. I'll be sharing more similar videos in the future, so subscribe to stay tuned.